In this video, we're going to cover formula weights, which is topic section 3.3 of the chemistry textbook. Kind of just a general introduction to this topic, every time you see a chemical formula or an equation, they all have some sort of quantitative significance or numerical significance. So what does that mean? It just kind of relates that the subscripts and the coefficients, which are found in chemical equations or even just like in the written formulas, each represent precise quantities and exact numbers. And then when we go in to determine the specific masses or the formula weights, which we'll learn later, we can indirectly determine the numbers of the molecules and the atoms in these chemical formulas, and then by using those we can relate them to molar conversions or different other kinds of conversions that we'll use later in the year. So the first kind of definition is the concept of a formula weight, which is also abbreviated to be FW. And the general definition of a formula weight is the sum of all the atomic weights, abbreviated AW, of the atoms in the chemical formula of a substance. And again, you need to remember the fact that atomic weights are going to be what's found on the periodic table, and you can either round these off to 1 or 2 decimal places. As you can see down here, they were just rounded to 1, which is typically 3 sig figs, but that just depends on what you're trying to obtain in the question. And then just kind of like the general concept of how to calculate it, we're going to look at this sample equation here, which is the formula weight of H2SO4. Now essentially what you're going to do is you're going to take the moles of each element, so there's 3 elements here, and you're going to multiply that by the atomic weights of these specific atoms, or the specific elements. So in this case, there's 2 moles of hydrogen, and you're going to multiply that by the atomic weight of hydrogen, which is about 1.0 AMU, or atomic mass units. And then you're going to add those all up with the sum of the atomic weights of sulfur and the atomic weights of oxygen relating to this specific formula. So here you can see that there's only 1 mole of sulfur in here because there's no subscripts or coefficients saying otherwise, and that's why we don't have anything multiplying in front of here. And then in front of the oxygen there's going to be 4 moles of that, so that's why there's a 4 here corresponding to this. And then again, all of these are found on the periodic table, and when you sum those all together, you're going to get 98.1 atomic mass units, or just AMUs for the formula weight. And then kind of looking at different ways to state the formula weight, you have the molecular weight, or MW, which is a little more specific, and it's basically just if the chemical formula is of a molecule. So for example, this sucrose down here is a molecule, and then the formula weight is also called the molecular weight. So essentially this is still the sum of the atomic weights, you're just going to be labeling it a little differently in terms of terminology. So again, here you're going to take the number of moles of each element. So here there's 6 moles of carbon, 12 moles of hydrogen, and then 6 moles again of oxygen. And you're going to multiply that by the atomic weights, which are found on the periodic table, to get 180.0 AMUs. And then the last kind of variation of formula weight is going to be ionic formula weight, which is obviously the formula weight of an ionic substance, and you determine it in the same way. So you're looking at the types of atoms and the atomic weights of atoms in the empirical formula. And then just kind of a more specific breakdown for when you're supposed to use the ionic formula weight as opposed to molecular or just general formula weight. And that's going to be in an ionic compound such as calcium chloride. So in this compound there's going to be 1 Ca plus ion and then 2 Cl minus ions, which is what makes it an ionic compound. And then again, you're going to calculate it the same way. You're going to see 1 mole of the calcium ions and then 2 moles of the chlorine ions, and you're going to multiply those by the corresponding moles with the atomic weights. And then that's going to give you this total answer here. Moving on to percent mass composition, which is also covered in this unit because it relates directly to the formula weight. The direct definition of this is going to be the percentage by mass contributed by each element in the substance. And it's also known as the elemental composition, which kind of just relates to the types of elements that are contributing to this general composition. And then kind of just like a real-world application of where you might see this, or in what types of fields specifically, you're going to see forensic scientists or even forensic biologists who are using this percent composition, which we're going to learn how to calculate, of some unknown powder that maybe you see at a crime scene or they needed to identify, and they're going to compare it to the percent compositions of other suspected substances, and that's really how they're going to be able to use to identify it. So that's just kind of a use that we can apply this concept to. And moving into how to calculate percent composition, you're going to need the formula weight of the substance, which we just learned how to calculate, the atomic weight of the element of interest, which is again going to be on the periodic table, and the number of atoms of that element in the chemical formula. So we're just going to look at the chemical formula that we're given or that we need to deduce from the written formula, and we're going to apply it to this equation down here, which essentially states the same thing. So you need the number of atoms of the element times the atomic weight of the element, and you're going to divide that by the formula weight of the entire substance, which is from the chemical formula, and then to get that in percentage form, you're going to multiply it by 100%. Looking at like some general strategies for these types of questions and also just questions in general, you want to first analyze the problem, so not necessarily drawing diagrams in this specific concept, but writing down important information like how many moles you have of each element. Then you're going to want to develop a plan for solving the problem, so this could be finding related equations and also the steps to determine whether you need the formula weight or the percent composition, something like that. And then you're going to finally solve the problem with what you deduced from analyzing and developing a plan. And you can often use dimensional analysis for this, but in this case you really just want to focus on checking sig figs. And then lastly, you're going to go into this and you're going to check the solution and just ensure that your answer makes sense. So kind of going in to apply this, we're going to look at a practice problem for formula weight. And the example it gives us is going to be calculate the formula weight of a calcium nitrate ion, or just calcium nitrate. And essentially what you're first going to do is you're going to write down the formula, which is CaNO3 because this is a charge of 2 and this is a charge of 1. So by crossing that, you're going to get this as the chemical formula. And then this poses another idea that if the chemical formula has parentheses inside of it, as it does here, then the subscript on the outside of the parentheses is a multiplier for all of the atoms inside. So we're going to show that correspondingly in our work down here. And again, we're just going to approach this in the same way as we did before. So for one calcium ion, or one calcium atom in this case, there's going to be 1 mole because there's no coefficients in the front and there's no subscripts affecting this calcium ion. So you're just going to get the atomic weights for that, and that's going to equal this. And then you're going to do the same. You're going to distribute this subscript of 2 here to the nitrogen atoms. You multiply that by the atomic weights, you're going to get 28. And then for this one, you're going to distribute the 2 into the 3 here, and you're going to get 6 oxygen atoms times the atomic weight, and you're going to get this. And then adding all these numbers up, you're going to get a total formula weight of calcium nitrate to be 164.1 atomic mass units. And then a similar question that it's going to ask you about percent composition. The practice equation it gives us here is calculate the percentage of carbon, hydrogen, and oxygen by mass in C12H22O11. And essentially, most of the time when it gives you a question, you're just going to have to calculate the percentage of one element, but this one is asking for everything to try to apply everything that we've learned so far. So first, what you're going to want to do is obtain the atomic weights of each element from the periodic table, as we've been doing. And then, as you can recall, the denominator is the formula weight of the entire substance here. And then for the rest of it, you have to do 3 calculations according to these 3 elements here. So showing the work for that, the percent of carbon is going to be 12, which is how many carbon atoms we have, times the atomic mass of carbon over the entire formula weight of this. And then multiply that by 100% to get your percent of carbon, or your percent composition of carbon in this element. And then you're going to do the same thing for the percent of hydrogen and the percent of oxygen. So as you can see here, this 22 is from the original equation, same with this 11. These atomic masses, or these atomic weights, are going to be from the periodic table. And then the denominator is the same in all of these because you're using it from the same general equation and the same general formula that you were given at the beginning. And then just don't forget to multiply that by 100 to get to your percentage here. And then a way that we can check to ensure that we did this correctly, you want to ensure that all of these add to 100%, which they do, which ensures that you did the equation correctly. And then here are just some independent practice problems, so if you wanted to pause the video and see if you can figure out how to get these on your own, but then I'm going to show you the answers for them. So this is going to be the answer for the first question. You can go through and you can see all the steps laid out here. This is the final formula weight that you were supposed to get. And then for the second independent question, you're going to determine the formula, calculate the molar mass of the compound, and then you're going to use this over the amount of nitrogen atoms to determine the percent composition, which is going to be 17.08%.